So we're going to try and do travelling wave solutions to this problem. Okay, so the numerical solution, I haven't fully gone into all the details of it, but you can see the code and I expect you to be able to sort of unravel it from there how it all works. But the travelling wave solution is our final thing to work out. So what we do is we assume that we introduce a travelling coordinate y is equal to z minus b tau. Okay, so b is the speed. Okay, we haven't used c because c was concentration. B is the speed of the wave. Okay, it was c before, but confusing, but we don't want another c here. So we say that alpha is a function only of y. We're assuming we're looking for ways that in beta is a function of y only. So the equation becomes d squared alpha y squared, okay, the z derivative of it. Or maybe just go back a second here, not rush this. Okay, so we've got the tau derivative of alpha is equal to the z derivative squared of alpha minus alpha beta. Okay, so the tau derivative is going to be minus v times, and we could have the but this could be a plus and we have it going the other way, so we'll just get a solution will be the same under some symmetry. The tau derivative is, so we get d alpha dy minus equals d squared alpha dy squared minus alpha beta. Okay, no problems there. And likewise, we get the same equation for beta, but we get a plus here. We get minus v, the beta dy is equal to, okay, I don't know why I've written this, with a partial derivative, it's d alpha, sorry, whoops, d beta plus alpha beta. Okay, so that's the system of equations here. That we've got to solve. So we're not quite to try and find the travelling wave solution. So this is a coupled system of PDEs. So we've got to try and simplify these somehow. And the first thing to do is to add them together. So what we get is we add them together, we get, think about that plus that, we're going to get minus v into the alpha plus beta dy is equal to d by dy squared of alpha plus beta. We get rid of this minus alpha beta term and we can integrate that immediately. So we get minus v times alpha plus beta is equal to d by dy of alpha plus beta plus some constant. And then this is the good old, it always comes down to the same equation, so this is this, an integrating factor equation or something like that, homogeneous or something like that. So you get alpha plus beta is equal to some constant plus, and I'm not sure it's the same as that constant there, I better be careful about that, times some constant e to the minus vy. So when we go on for our travelling wave solutions here, we want the solutions to be bounded at plus and minus infinity. So that means that C1 must be equal to 0 and alpha plus beta must be a constant. So that's going to simplify our equation. Whoops, I've written into the danger zone here, my face might start appearing. So bounded at plus or minus infinity. Okay, so it means that C1 is 0. Okay, so alpha plus beta is a constant. Okay, now we're going to assume for simplicity, because we non-dimensionalized in such a way that, we remember we started out the initial conditions 1, so we're going to assume that that is equal to 1, okay, just to make ourselves life simpler. So we can substitute here that alpha is equal to beta 1 minus beta. Okay, so that's going to get us down to a single system of equations when we substitute that into here. So we're going to attain the system of equations d squared beta dy squared plus b times d beta dy plus beta into 1 minus beta equals 0. Okay, so brilliant. And then we're going to analyze this using the old magic phase plane. So we introduce gamma as d beta dy and beta. And we look at the equilibrium points. So the equilibrium points, we've got to have, so I should write down a system of equations, shouldn't I, before I do that. So the gamma is d beta dy, and then d gamma dy. I'll just go back here and write it like this. The beta dy equals gamma, and the y is this travelling wave coordinate, is the coordinate that we're going to use. It plays a role of time in the analysis of these systems. The gamma dy is equal to d beta dy squared, so it's going to be equal to minus v times d beta dy minus v gamma minus beta times 1 minus beta. So we go in and then we find these equilibrium points for the system. So that's the equilibrium points are when everything comes out of the equilibrium. It's all about the equilibrium points in these systems. So what we get is gamma is equal to 0. Okay, and we get beta must be equal to either 0 or 1. So there's two equilibrium points at 0, 0 and at 1, 0. And we can analyze those equilibrium points. Okay, I'm going to talk to the notes here at this point here rather than going through it. So if we analyze these equilibrium points, so we end up with some sort of nodal sink or spiral here, and we end up with a saddle point here. You never get two saddle points or two nodes. You need a saddle and a node. So there they are there. And then there's this sequence of paths that connect the 2 points. So we've got to go and analyze and just try and understand this solution. Okay, and this is just to show you here how it relates to the travelling wave solution. It takes an infinite amount of time, or whatever the time variable is, to come out of here, and it flows down into here and produces this travelling wave solution. So the last thing to do is just to try and prove that this connection exists and a few properties of that.